All right, in this video we're going to be covering rational zero theorems, all about finding potential zeros. Now the rational zero theorems means we're looking for zeros that are fractions. That's what rational numbers are. They can be written as a fraction. So when you look at a polynomial function, again, in descending order, a sub n, this is the coefficient on the x sub n. A sub n minus 1 is the coefficient on the x sub n minus 1. All the way down to a sub 0. This is your constant, and the constant cannot be equal to 0. If it were a 0, you could factor out an x, and then we're going to work with that new leftover polynomial. The list of possible rational zeros, your x-intercepts, are the positive negative ratios of the factors of the constant over the factors of the leading coefficient. So you take the constant, you write down all its potential factors. You take the leading coefficient, you write down all its potential factors, and you build fractions, and you make them plus or minus, and those are your possible rational zeros, your possible integers, x-intercepts. All right, so let's practice one here. Find the set of all possible rational zeros. So here my leading coefficient is 2. My constant is 12. We don't care about anything in the middle. So the factors of 12 are 1, 2, 3, 4, 6, 12. 1 times 12, 2 times 6, 3 times 4. The factors of 2 are 1 and 2. So to build my fractions, 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. When you have that 1 as a factor in the denominator, you can just rewrite everybody in the numerator. So plus or minus the set. Here's my possible answers. There's my numerator, 1, 2, 3, 4, 6, 12. Now your other factors down here may generate reducible fractions to answers you already have, and you don't have to list it again. So starting with the 1, 1 over 2, that's 1/2, I need it. 2 over 2, well that's a 1, I already have it. 3 over 2, that's 3/2, I don't have it, I need it. 4 over 2 reduces to 2, 6 over 2 reduces to 3, 12 over 2 reduces to 6. So this is my list of possible rational zeros. Now what I'm going to do is I'm going to list these in order. So negative 12, negative 6, negative 4, negative 3, negative 2, negative 3/2, negative 1, negative 1/2, positive 1/2, 1, 3/2, 2, 3, 4, 6, and 12. All right, now what I'm going to do is we're just going to put this on the back burner for a second, and I'm going to talk about the types of division. So when we factor our polynomials, it's all about division. So polynomial division, f of x divided by g of x, we can write g of x out front, f of x on the inside, because what we're trying to do is factor out possible factors. Now when you do division, your q of x, this is your quotient, r of x is your remainder, g of x is what we divided by, called your divisor. The factor theorem states that if you were to do polynomial division, and if your r of x right here is a remainder of 0, then this g of x is a factor of f of x. And then you could rewrite your f of x as x minus some constant. Let's say that's what we factored out. This is going to be, this will be your polynomial. And then this would be your, what you divided by. So what we're going to do is we're going to keep finding binomial factors. And what I was kind of discouraged about is that they actually wrote this backwards. Because they say you want to divide by g of x. Okay, well, what you really want to divide by is a binomial factor. And you divide the binomial into f of x, and then your quotient of x is multiplied by that binomial factor. So they should really have written this as q of x times x minus c. And we're going to repeat this process, then take whatever your quotient was left over, and we're going to divide out another binomial factor until we have this thing completely factored. So here's an example of what I'm saying. So here's my polynomial factor. X cubed plus 6x squared plus 11x plus 6. This does not factor by grouping like we did earlier. So what I would have to do is, because my leading coefficient starts off with a 1, there would be a 1 in my denominators here. Then I just need to look at all my factors of my constant at the end, which is 6. So 1, 2, 3, and 6, plus or minus those numbers. So I'm going to try x plus 1. Now, I've already worked this out, so I know this is going to factor. But just to show you what I'm saying, how this factor theorem works. We take this binomial, you take the x, you divide it into x cubed. That's the only division you do. You don't divide by the 1. You only divide leading terms. So x cubed divided by x is x squared. Line that up over the x squared, multiply that to everything in front. So you get x cubed plus 1x squared. Now we subtract both terms. And the goal here is to cancel out the leading term on the inside, which we're doing. 6x squared minus 1x becomes 5x. Bring down the next term. Now 5x squared is your new leading term on the inside. Take 5x squared, divide it by the leading term on the outside. 5x squared divided by x is 5x. Line it up over the x term. Take 5x, multiply it to everything out in front. 5x times x is 5x squared, 5x times 1 plus 5x. Again, subtract both terms. Leading term cancels. 11x minus 5x is 6x. Bring down the plus 6. 6x is the new leading term. Divide by x. That's a positive 6. 6 multiplied to x plus 1 is 6x plus 6. You subtract, you get a 0. Now we have this polynomial is equivalent to our quotient, x squared plus 5x plus 6, multiplied by x plus 1. So now that I'm taking this cubic function, if you will, and factored it down to where one of the factors is a quadratic, and I recognize, hey, I can factor this. 2 factors of 6 that add up to 5 are 2 and 3. So now I factor this further, and here's this polynomial factored down to these 3 binomials. So that's what our polynomial division is going to be used for, to help us factor these polynomials. Now, I'm going to be the first to admit, this is a lot of time. We don't want to do this. That's why I didn't leave any room in your notes to write this down. We want to do synthetic division. It's much quicker and easier. Now, when you want to divide by x plus 1 into this polynomial, my synthetic division technique is a little bit different than the authors. They're the same, but I like and understand my technique better visually. So x plus 1 has to be solved. You set it equal to 0, x is equal to negative 1. So in the top here, you just take the coefficients off of the top. 1, 6, 11, 6. Keep everything lined up. just like we had everything lined up here in our polynomial division. Then, like I said, we take the x plus 1, put it up here in the upper left-hand corner, set it equal to 0, solve it for x, move the negative 1 down here on the bottom. The author has it up here on the top. I don't like it up there. My eyes have to move too far around to what I want to do. So the first thing in synthetic division we do is you drop down the 1, and then you're going to take whatever number you have here in the lower left-hand corner, and you're going to multiply this rational 0 that we're working with to the 1 and line it up into the next column. And then you combine and add this together. So negative 1 times 1 is negative 1. Add this together. 6 plus negative 1, or 6 minus 1, just combine it, is 5. Repeat the process. Negative 1 times 5, negative 5. Combine 11 minus 5 is 6. Negative 1 times 6 is negative 6. Combine it with the 6 is 0. That's your remainder. Now this becomes the constant, the x to the first, and the x squared. Because we reduced and factored out an x, all those x terms have to reduce by 1 in the power. You get to your quadratic, you factor it, you have the answer. So this is going to be our factoring technique. Now, upper bound, lower bound tests. This is how you find this stuff by hand, if you will. So a lower bound test is a way to reduce all, I don't want to say all, but let's say some of those lists of rational zeros, and we don't have to test them. So in order for a lower bound test to work, when you test a rational number here, and if you get alternating signs on the bottom, then this 0 is a lower bound. That means nothing in that numerical list I generated earlier that I said I put on the back burner is not a possible 0. But to get alternating signs, you have to use one of the negative rational zeros. So you have to have a negative number out there. Now the upper bound test, this is what you want to see, all positive signs on the bottom. If you put a positive rational 0 out in front, you get all positive numbers, then anything bigger than this rational number is not going to work because you found an upper bound. Very similar to when we were talking about on the calculator, what's the lower bound, what's the upper bound, and we only test what's in between. The same concept. Okay, 0, if you get a 0 anywhere on the bottom, you can be used for any sign that you need. So if I have, all right, here's 2, 0, 3, minus 5, so on and so on and so forth, I needed this to be a negative, so since it was a 0, 0 is considered neutral. It doesn't have a sign, so we can let it be the negative. Or if you have 0 here, that can be the positive. Same thing over here. Any zeros over here will count as a positive. All right, so off the back burner, back to the front, start to cook again. Here was that polynomial function. It doesn't factor. This was my list of rational zeros that I could possibly have. So what you'd want to do is let's test a lower bound. So we have to use a negative number here. Now, what I would do here, here's the midpoint. Well, -1 would be easy to work with, but the problem is you want to probably go about halfway into your negatives. So I'm going to start with -2. So I'm going to test to see if all the signs alternate down here. So I bring down the 2. Negative 2 times 2 is negative 4. 7 minus 4 is 3. Now, a lot of people will tell you, well, stop, you don't have to go any further. It's not a lower bound, which is true because my signs aren't alternating. However, we may have gotten lucky and negative 2 was actually a 0. So you keep going all the way till you get to the remainder. Negative 2 times 3 is negative 6. Plus negative 7 is negative 13. Times negative 2 is 26. Okay, we didn't get a 0. This is not a factor. Your signs are not alternating. So here's an example of doing the lower bound test. We'll come back to that in just a second because now I want to demonstrate the upper bound. So upper bound, you choose a positive number. Again, all right, I'm going to go this time with 3. My 2 is unlucky here on the left. I'm going to go with 3. So we bring down the 2. 3 times 2 is 6, plus 7 is 13. So far, so good. They're all positive. 3 times 13 is 39, minus 7 is 32. Still positive. Keep going. 3 times 32 is 96, minus 12 is 84. 3 is an upper bound. The signs are all positive. So what that tells me, I don't have a 0 here for a remainder. The 3, the 4, the 6, and the 12 are not possible zeros. They're out of my list. Okay, so that's what we do the lower and upper bound test do to see what numbers we can eliminate. Now, over here, let's go back to the negatives because we didn't find a lower bound. Don't go to negative 3. Skip a number to negative 4. Because if negative 4 is a lower bound, then you automatically know negative 3 will be a 0. If you test negative 3 and it's not a lower bound, then you got to be testing negative 4. So, okay, let's test it anyhow. Try to limit the work. So I'm going to negative 4. Bring down the 2. Negative 4 times 2 is negative 8, plus 7 is negative 1. All right, things are looking good. My signs are alternating. Negative 4 times negative 4 is negative 1. That's positive 4. Minus 7 is negative 3. Negative 4 times negative 3 is positive. Whoa, wait, check this one out. We got a 0. We found a factor. Even though it's not a lower bound, my signs didn't alternate, but I kept on going, and I found a 0. So negative 4 means that, okay, turn that into a binomial. X equals negative 4. That's x plus 4. And this is now your constant. This is your x to the first. This is your x squared. So 2x squared minus x minus 3 is my trinomial, which is quadratic. And now if I want to, I can test my quadratic rules for factoring, and it factors to these two binomials. And there's all my true zeros. I had a list of possible zeros. And then I go through that list to start finding rational zeros to make smaller polynomial functions. And our goal is to get it to a quadratic to see if we can then factor it further, which a majority of the time they will, and you get the rest of your zeros. All right. Now, this is what we have to do when we didn't have calculators. Now that you do have calculators, just graph it. All right, take the 2x cubed plus 11x squared minus 7x minus 6 and graph it. Now, the one thing in our graph that we can use is, since our constant is 6, you know that your rational zeros have to be from negative 6 to 6. So a standard window, which goes from negative 10 to positive 10, will fit all your x-intercepts that you're looking for. So I graph it. So I hit zoom 6. Here's my graph. Now, since my graph is counting by ones with the tick marks, I can just start counting my tick marks to find my zeros and start typing them in to make sure the y is a 0. So we're just going to count tick marks. So 1, 2, 3, 4, 5, 6 to the left, -6, I typed it in. It says y is a 0. There's an x-intercept. That's one of them. Next, going to the right, I hit this tick mark right here. That's a 1. Type it in. There's an answer. Now here, I'm somewhere between -1 and 0. Okay, well, look at my list up here. My leading coefficient is a 2. So that means my denominator factors are a 1 or a 2. So the only possible rational number with a denominator of 2 between -1 and 0 is a -1/2. So I typed in -1 divided by 2, and the calculator tells me -0.5, y is 0, and there's my third 0. All right, so there's how we find your possible list of rational zeros and how we're going to use synthetic division to find more zeros to do our factoring for us.